Sorry about that. I'm not timing these videos very well. I need to distribute this 2 to get rid of the fraction, and so that's going to give me 2 times y squared is 2y squared. 2 times negative 3 halves, that would just be negative 3x squared. And then I don't need to write 2c. Again, there's that idea that c is just a constant, and so saying 2 times a constant, it's still a constant. Okay, so just c. And then we pretty much have our answer now that we verified the solution. As long as I add over the negative 3x squared, then I'm going to end up with something that looks like what was given in the original equation, okay? So I have verified that this is a solution. And then part 2 to that was find the particular solution that satisfies the initial condition when y is 3 and x is negative 2. So I'm going to use this equation here, and I'm going to plug in 3 for y and negative 2 for x to find the value of c. And then this would be what? 4 times 3, so 12. 9 times 2 would be 18. So it's looking like C is 30. So then my final answer for the particular solution would be 3x squared plus 2y squared equals 30. Okay, let's skip that one. All right, so we're going to take kind of like a hard left and change to a different topic of discussion within the differential equation category. And so this is kind of an easy, cool thing that we're going to learn. It's called a slope field. And so basically, you guys know that dy dx means slope, right? And you know that dy dx can change at any point in time on a curve. So what we have here is we have a differential equation, and I'm going to create a visual aid to help me understand the slope at different points along the curve. Okay, it's a visual just to help you understand options for different solutions to a differential equation, but like without doing all the algebra. Okay, so essentially what will happen is you'll have a differential equation. So right here, dy dx equals 2x. And you're going to sketch a slope field by basically picking different ordered pairs and saying what the slope would be at those locations. So I have a graph already set up here. I'm going to pick different ordered pairs that I can see on this graph, and I'm going to find the slope of those points. So I don't know, maybe I'll start all the way here in the top left. This would be negative 2, 2. So negative 2, 2. Then if I pick that ordered pair, what would the slope be? Well, the slope is dy dx. So you would find this value by plugging in your ordered pair, either all or part of it, to the equation. So the ordered pair, or I'm sorry, the derivative says it's equal to 2 times the value of x. So you would need to just do 2 times the value of x to find the slope at that location. So it'd be negative 4. And I would continue doing this for various ordered pairs along the curve, and I would actually want to find the slope at every single one of these little black dot things all the way through my graph. I don't know why I chose to write it in this order. That was crazy. So let me go back and make this more organized. So I would need negative 2, 2, negative 2, 1, negative 2, 0. Basically just every ordered pair on that graph, I would need to find the slope at that location. This XY table is not really necessary because the equation is just 2 times the value of x. So I don't know that I really need to write it in a table, but I'm doing that for you just to give you a visual. So at negative 2, 1, the slope is, remember, according to the equation, 2 times the value of x, and so that's negative 4. And actually, all of these have the same x value, right? So they're all going to have the same slope this time just because of the way the differential equation works. So let me pick a different value just to have something to compare to. And so like if I'm at location -1, 2, the slope there would be 2 times the x value, which would be -2. And then same thing for 0, 0, 2 times the x value would be 0. All right, then here's what you do next. You go to your ordered pairs, and you're going to identify the slope by drawing a tiny line segment. And so if at -2, 2, the slope is -4, you're going to draw a tiny line segment. Maybe that's not drawn very well, but a line segment that has a slope of about -4. So I drew mine down to show negative, and kind of at a pretty steep angle to show that it's a fairly steep slope of -4. And I would want to repeat that all the way through all the ordered pairs that have a slope of -4. Like this. Nope, not like that. All the -2s. Oh, Lord. Okay, I'll figure this out eventually. All right, I think I've got it fixed now. Okay, so I need to continue making little line segments to represent the slope at that location. So the slope at -1, 2, we found to be -2. Now I'm going to make sure when I draw this line segment that it is still going down, but it's not as steep as the -4 line segment, okay? And this is just do your best to make it look like it's not as steep. And notice I made all of these -2 slopes because all of these have an x value of -1. And so they would all have the same slope because of the way the equation is set up in this question. What about all the zeros? The zero slope, if I plug it into the differential, 2 times the x value would be a 0 slope. So any 0x coordinate is going to have a 0 slope, which is just a little flat line. Okay, continue plugging in. All of these points have an x value of 1, and if we plug those in, you would get +2. So I need a little line that's a positive slope, about the same steepness as this guy, but obviously in the positive direction. And then the last one is x values of 2, which would have a slope of 4. And so it needs to be, again, a positive little line segment, but about the same steepness as the -4s. So voila, we have a slope field. And so the slope field is going to show the way that the curve is going to move throughout the coordinate plane, even though we don't necessarily know like what the initial condition is for the curve, we know it's going to have this general shape. So if you look at the left side, the slope is going down, and then the middle is flat. So this would be like a max or a min. Actually, it would be a min because it's going down before, and then back up. So this one actually looks like it might be kind of a parabola shape. Oops. Okay, here's another one. I just want to show you one more just to run through how this works. This one has a different equation. So my differential equation is the derivative or the slope is 3 times the x coordinate minus 2. Okay, so like if I pick -2, 2 as my starting value, 3 times the x value would be -6, minus 2 would be -8 for the slope. If I pick -2, 1 as my starting point, 3 times the x value is -6, minus 2 is still -8. So any of these -2 x coordinates are going to have a -8 slope, and it's really hard to draw a -8 slope. It's just got to be a super steep, almost vertical line. -1, 2, we'll use that as our first reference. So any of these -1 x values, plug it in. You'd get -1 times 3 is -3, minus 2 would be -5. So again, really steep. I just need to make it look slightly less steep than the lines before it, which is tough to do. Just do your best. Let's say I'm at 0, 2 now. So I'm up here. I want to find the slope there. 3 times the x coordinate would be 0. Minus 2 is negative 2. So again, a negative slope, but definitely not as steep as before. Okay. What about like 1, 2? So 1, 2 would be 3 times 1 is 3, minus 2 would be 1. So now we have a positive slope. Okay, just do your best. And then we've got, what, 2? So 2, 1. Let's see, 3 times 2 is 6, minus 2 would be 4. So we want a 4 slope, a positive 1, I don't know, maybe like this. Okay, so this one's interesting. Got a really steep slope over here, and then it starts to flatten out. I'm guessing it would hit 0 somewhere between x equals 0 and x equals 1. Okay, almost done. So here's what we're going to be doing. The last thing is kind of like reading slope fields. So look at the slope fields, kind of see like the pattern to the lines, to kind of distinguish what the graph is doing. So this one says match each slope field to the equations below. And so this one, what I would do is just pick some x values, or not x values, some ordered pairs, plug them into the equation and see what matches. So like this one, maybe I'll start up here. This ordered pair would be negative 2, 2, right? And that is definitely a negative slope because the line is going down. So I'm going to plug this x and y value into each of these equations and see if any of them give me a line that would be going down about this steepness. So like 1 and 2 are not going to work because, well, no, 1 and 2 might work because I need to plug in a positive and a negative. Let me think here. So if I look at equation number 1, the y over the x would be negative 1, which that could be a negative 1 slope. Number 2, the x over the y is also negative 1. Okay, so then we're getting the same answer for 1 and 2, so then it must be another point that's different. So if you want to stop and look closer, graph A and graph B both have negative slopes in that area, so equation 1 and equation 2 could be either graph A or graph B. So maybe we should find something that's different about graph A and graph B to compare in that way. I think what I'll do is pick a point that's closer to the x or y axis, because it seems like the closer we get, this one has a more flat slope and this one has a more steep slope. So let's try that. Maybe I'll just call this like, what would that be? Negative 1/2 and positive, I don't know, 2. We'll plug those in. Okay, so negative 1/2 and positive 2. The y over the x would give me negative 4. That doesn't look like negative 4. It's not nearly steep enough, and that would be for equation 1. But equation 2 would be the x over the y, which is negative 1/4. That looks like it's correct. So that means that equation 2 will match with graph A. And that means equation 1 must be graph B. And you would just repeat this process for the options C and D down here. Just kind of pick a location where it appears that their slopes are significantly different. I don't know, maybe like this one looks much steeper than that one, but they're in the same location. You with me? Okay. This one I'll walk through really quickly. This is going to be reading a slope field and using an initial condition. So you're going to start by putting a point at 0, 1. and you're just going to kind of follow the curve to sketch this graph, but you have to go through that point. So this looks like I have almost a horizontal slope. It's getting more flat if you look at the slope field, and then almost flat here